Test 1, 2. We're just working on getting the projector up here.
Now you're on. Please leave the projector on.
Test 1, 2. Yep.
They still have problems with the projector, and I'm really wondering why it doesn't show up in the meeting. Because no, it doesn't. Okay, so people can't see the slides, but we can still kind of start with introduction stuff.
So that's the request. Yeah, requiring.
No, something else.
Today,
On the small one, right?
I know the big one is coming.
Great.
this is two criteria for a lot of things.
Right.
This one that's projecting, right?
No, it's here.
It's just unplug the HDMI cable and plug it back in.
It's coming out here. It was not super bright, but it was coming out.
Yeah, I'm aware. Thank you.
Also was not.
That's what we're trying to do.
Yeah, we trained him yesterday.
Stack the door down. Push it into the.
We're expecting those people. So this week, so new laptop.
Yeah.
And it cycles through. Yesterday. This is so dark and so bright. I think, new laptop, you go down.
So it's a bright reflection.
Yeah. Yeah, it's like, and then it's from the week from there.
I know where that is. Go there, it's like, it's like the national campus. About the big thing. The big thing. Remember you come into the house and you driven to get to the place where it is.
It's there. It's going to be wrong for your comfort monitor, but it'll be right on the projector.
Okay.
Which is probably a bit better. Let's try that.
Thank you.
Just do it because you'll actually hear it.
All right. Everyone take their seats. We're going to get started. We're running a little bit late already. So. Okay. Jason, who's up first? Can you be ready to go?
Still not right, sorry. Let's try. I'll just try to adjust this.
All right. We're going to get started. So welcome, everyone. This is the Measurement and Analysis for Protocols Research Group. I'm Dave Planka, and this is Mirya Kuluin. We're your co-chairs. We have a packed agenda in our 2.5-hour time slot, 11 presentations this morning. So I'm going to ask the next speakers get ready to come up right after when the person's closing up. and we'll have you up here. You'll have a clicker to change your slides. We have the slides on the common laptop here. We'll spin through the introductions. So the IRTF uses the same note-well and intellectual property process that the IETF does. That's there. Here's a bunch of links to our charter, the mailing lists. There's an Etherpad for note-taking, and the slides are all posted. So,
Yeah, thanks to the note takers, Matt and Lars.
Yeah, Matt and Lars, thank you. So the way we put together the agenda for this meeting is, again, the call for contributions on the mailing list that we put out on February 1st. We received about 15 proposals, of which 11 you'll see today. Just a couple were out of scope for Maprg, and the others we've asked the people to present at a subsequent meeting when it might be more convenient, and also to fit the times we have. Thanks for sending that stuff. Again, we're soliciting for future meetings. You can advertise your projects here. If you don't have measurement results yet, we'll put them in the agenda, and there'll be a couple advertisements at the end of this. Again, I'm not going to go through these right now just to save time, but 15 presentations, and we'll introduce them as we go along. 2 announcements. The Applied Network Research Prize has been awarded for, I think, to 6 people for 2018, 2 of which we'll be presenting tomorrow morning in the IRTF open meeting. So please join us for that. Really neat opportunity to see some of the best work from the academic conferences presented in this forum. The other thing that's going on in the IRTF right now is the Applied Network Research Workshop. The call is out now. The paper submission deadline, it can be existing work, is April 20th. I mean, previously published work, April 20th. And that will be happening at the next IETF in July in Montreal. So we're going to come up, or start with our first presentation here. And we're starting off with a couple of presentations that are just heads up talks that we think are important for this this audience to hear something about. So this is Jason Livingood. You're up, Jason.
Great, thanks very much. I'm Jason Livingood. I work at Comcast and North American ISP, and I thought I would give a quick talk about, is there a way to get it on this screen as well? Quick talk about measurement challenges in the gigabit era.
Yeah, it's also not on.
Yeah, it's the mirroring.
There we go. Great, thanks. So measurement challenges in the gigabit era. So a view of some of the impacts that measurement have on things like network operators. So as background, I certainly recommend this paper from some folks at MIT a few years ago. There are, in essence, a wide range of existing systems. They really fall into 2 primary camps. One which run automated measurements from homogeneous gear that's at customer homes. Most of these are national systems installed by regulators. For example, SAMNOS, which is based in the UK, used by Ofcom, FCC, and a bunch of other regulators around the world. Of course, there are also user-facing systems, usually web-based, like speedtest.net. And both of those, from my standpoint, are starting to show some, interesting behaviors as we approach a gigabit per second at the edge in the access network. We're starting to see some issues which we'll talk about now in the sort of multi-hundred megabit per second era. But in our network, at least, many of our customers are 1 to 500 megs, and we offer 1 gig now, but the bulk of our customers will start to move to that in 2019. And lastly, measurement systems today focus primarily on speed, but end user expectations about their internet services are changing a lot. Measurement systems that are sort of customer facing haven't caught up yet to that. They're really still focused on speed. Customers are caring more about reliability, availability, and other performance of app services. So what are some of the existing issues that we're seeing in the systems that are out there today? One, most of those systems were designed with an assumption that the bottleneck link is in the access network or in the home network. And the entire design of the system is oriented towards trying to measure that. Unfortunately, as we enter this sort of gigabit era, the home network Wi-Fi is usually becoming pretty good with a mesh Wi-Fi in the house. And the access network is usually 1 gig. That means that the bottleneck link has moved off to primarily an interconnection link or to the application servers where the tests are destined or something in that data center network. But the tests really, the designs of those tests really haven't evolved yet. And so in many cases, we're finding that the bottleneck link that people believe is being measured is a different link. And so in the multi-hundred megabit era that we're in today, we're seeing a 20 to 30% negative impact on occasion on some of these tests, which is significant. And of course, why does that matter? You know, a lot of regulators and state's attorney general and others have financial consequences if operators aren't meeting these tests. Users certainly use them for troubleshooting. So there are significant financial impacts to negative results in these kinds of things. So in terms of key questions that we've been asking some of our measurement partners and measurement researchers is, you know, does it make sense to continue this sort of test where you're running from, you know, one sort of test or multiple TCP connections to one destination site? There's no resemblance whatsoever to actual user behavior anymore in that test, and there are really no application services at the edge that use 1 gig. So in a way, what's the point of a single test to a single destination of 1 gig? Maybe a more appropriate is to spray hundreds of tests simultaneously across hundreds of destinations. But it also prompts questions about, you know, the underlying, you know, design and how you report your responses out and so on. You know, and of course, even today, you know, how can a lot of that server infrastructure be better and more independently, transparently monitored? For example, in the US, we've used RIPE Atlas probes to measure the SAMNOS infrastructure, and you know, they sort of outsourced that to some other providers like MLabs, and have found really interesting variations in availability uptime that aren't really apparent to even regulators or operators. So there's a lot of variation at the server side that can affect the results as well. And of course, a key question that we always have asked in an operator environment is, you know, when will the test away from simply testing throughput tests move and start looking at latency and reliability and other things, bearing in mind, of course, that the things that are measured pervasively are the things that network operators design to, the things that they market to, and then the customers start to pay attention to buy. So in a way, the things that start getting instrumented in measurement may eventually make their way out to the way that services are marketed and so on. And of course, the last couple of points here, QoE is as much impacted by sort of speed, as if you will, and network operator sort of access network performance, but also application or edge performance. And so, you know, we've contemplated measuring those things as well. And then lastly, you know, as I mentioned before, the things that you measure, you're going to incentivize. So even in the beginning of things like the SAMNOS testing in the US and in the UK, it fundamentally changed the way that operators were provisioning capacity in the network and the way they were you know, offering services. It wasn't just up to, and you would hope that you would get a speed once a day, but an expectation that you'd get your speed at, you know, peak hour and off peak. And so whatever gets measured is what you'll incentivize. So, you know, my question, of course, is, you know, BCP 38 and other kinds of things might be interesting to measure. And we'll hear some of these things today about IPv6 and DNSSEC, you know, things that are more nuanced about services.
Thanks, Jason.
Thank you.
We probably have time for one question or comment. Anyone? Okay, thanks a lot, Jason. Luke, you can come up. Oops. All right, next up we have Luke Hendricks talking to us about some visualization stuff you did in the hackathon, right?
Yeah, that's correct. Good morning all, I'm Luke, I'm with University of Twente. I like to measure things v6. This is running automatically right now and spoiling all of my surprises. Could you? Thank you. So yeah, I've been attending the RIPE v6 hackathon, I think 4 or 5 months ago, and this is kind of like a spin-off from that. So yeah, this will work. So problem with visualizing v6 stuff, we cannot really use what we have done for v4, right? Which is often true for things v6. You probably have seen one or both of these visualizations, either XKCD or some of the work at ISI by John Heidemann and his colleagues. We can visualize the entire V4 space in something that's, still readable, if you will. This is a Hilbert curve, a space filling curve, showing the entire V4 address space. If you want to do the same thing for V6, it's quite useless. It ends up like, something like this. You will see a small dot representing the 2000/3 space. This is useful to convince people that indeed we do have enough address space in V6. Other than that, I think it's quite useless, right? So I have created this tool called sesplot. Ses means 6 in Dutch. This is based on scarified tree maps. You can look it up in this footnote, which basically means is that we will always fill the same space regarding of our input set. I will show you some pictures, but we use the size to depict the size of the prefix, and we use colors to depict how many addresses of our input set are in this specific prefix. And instead of plotting all the V6 address space, we only plot what we feed it, right? This way we can look for outliers in, for example, measurement data or HTTP exit logs or whatever, right? So picture time. This is a visualization from sesplot based on all the announced prefixes. So this is 46,000 prefixes as seen by route views. And for the addresses, I used a hit list that the guys at the TU in München make, right? So what you see here is that the bigger prefixes are in the top left corner, and we fill up the entire plot with all the smaller, more precise prefixes. We then color all the squares according to the number of addresses that we've seen in our input set, all right? So what we can see here is that for the entire announced prefixes, there is still some white space, right? Which means that on this hit list, there are no addresses within these announced prefixes. So now you can say something about how complete is this hit list, yes or no. There is some white space, although there's a lot of stuff is there. If we want to look at what is only in prefixes that are represented by this hit list, we can filter it out. And we get I think a more fancier picture. And now you can, for example, spot for outliers, right? You see a big red square on top, which is a bigger AS with a lot of representation. So you can reason that this might be a overrepresented prefix in your data set. Well, there's more things to spot, but because of time, I will skip some things. Another thing, measurement I did a week ago on open memcached instances on V6. I found 361. And the interesting part here is that you can spot some smaller prefixes that have a lot of them relatively, right? That's the bright red square on the lower right corner. So one of the features I built into this thing is that we output to HTML with some interactive stuff. You can zoom in on the plot. You can have some extra information and tooltips, which you can see here on this screenshot. So that way you can get more out of plots that are very dense. And I mean, they still become very dense, right? If you plot a lot of prefixes with a lot of addresses. And that's basically it. This tool is now in a very generic state, if you will. You feed it a list of prefixes, you feed it a list of addresses, and that's it. And I'm wondering where to go from here, right? There's probably a lot of use cases that I didn't think about, and I want to continue working on this thing because I think it's quite nice. But I would like some input to see where this can go. It's under an MIT license on GitHub. It's written in Rust because I like Rust. But this is basically the most important sheet, maybe. Please try it out. If you see any, nice use cases in this, please let me know. I will be here all week, so please reach out to me either in person or via email. If you want to see any features, tell me or make a GitHub issue or whatever. Thank you.
Thanks so much, Luke. While there's time for one question or comment, while we set up Roland, if you want. What I think is one of the things that's interesting about that is transitioning from the tool to a useful measurement, and I think you got a good start on that by being able to show, for instance, where memcache stuff is. Mm-hmm. Thanks, Luke.
Okay, thank you.
And here's Roland. So the next two presentations are going to be updates on things that were at Maprg before. So one of our goals in this is to keep bringing you the data back again and again and again. And Roland has been one of those that's visited us a number of times and can keep us up to date on what's going on with DNSSEC.
Yep. Okay. Thank you. Yeah. So this will be a quick update on measuring DNSSEC deployment with a focus on the quality of DNSSEC deployment, and it's shared work with Northeastern University, SIDN Labs, and SurfNet. So the goals we've been measuring DNSSEC deployment for a long time, and one of the things that we observe, that everybody observes, is that in the general population, DNSSEC deployment generally remains low. Right? It's around 1% in ComNet and org. And then there are some CCTLDs that do much better. For instance, .nl and .sc both have almost half of all their domains signed with DNSSEC. And this is likely because they incentivize DNSSEC deployment by giving registrars some reduction in the price for registration. Now, what we wanted to study is if organizations that do deploy DNSSEC get it right, both in the general population, but also in the CCTLDs that have a much larger DNSSEC deployment. And the graphs in this presentation are based on 2 papers, and the references are on one of the final slides if you want to read the papers. We used longitudinal data from the OpenIntel platform. Go and have a look at our website if you're interested in that. We measure almost 60% of the entire namespace on a daily basis, and we record that data, and we now have some over 3 years of data collected that you can use to analyze the state of the DNS from day to day. And we have a new website coming soon. Now, for the ComNet.org study, we used 21 months of data, and for .sc and .nl, we used about 1.5 years of data. And we had a number of challenges when we were doing these measurements, because what we wanted to do, if you want to see if DNSSEC is done right, you need to validate all the signatures, and we really had to validate millions and millions of signatures. And also, we wanted to see if people do the more complex stuff in DNSSEC, such as key rollovers, so we had to track DNSSEC key rollovers over time, and that was actually quite challenging to do for such a large data set. So for that, I'm not going to go into detail, but we used some, say, quote-unquote, big data technologies, a Hadoop cluster with Spark on it, so we could validate all the signatures. And if you want to learn more about that, read the papers. Now, if we look at the general population, ComNet.org, this shows you a graph over almost 2 years of the development of the number of signed domains in .com. And the takeaway from this is it's low. Right, .org is the highest. Around about 1% of domains in .org are deploying DNSSEC. And for Common Net, it's a little bit lower, but it's also sort of going towards the 1% mark. Now, this data is almost a year old, and I can tell you that since then, not a lot has changed. It's still around this mark. But this isn't the whole picture. If you look at it, the previous graph shows you domains that have signed their zones, but up to 30% of those don't have a secure delegation in their parent zone. So that means that they've gone through all the trouble of deploying DNSSEC, and then they didn't create a secure delegation, so nobody can validate their signatures. So that's just plain stupid. Why would you do that? And we have another paper that I realized that I forgot to cite in this that actually looks at that in a little bit more detail. But it turns out that many of these signed domains in ComNet and org are actually side effects of the incentives in the .nl and .sc CCTLD. So these are people that deploy DNSSEC for all of their domains, and they also do it for ComNet org domains that they have, but then they don't bother to create a secure delegation in the parent zone. Now, we looked at errors in these deployments because we wanted to see if people do DNSSEC, do they get it right? And the most common problem that we found is actually missing signatures. So as you can see in ComNet and org, up until the end of 2016, up to 2% of signed domains were missing signatures. And basically that means that you break the zone. And it turned out that this was it was mostly one operator that was responsible for this, and what they were doing was that some of their name servers, if you sent them a query, they would give you back a signed response, including the signatures, and other name servers would give you back just a plain DNS response. And this really broke stuff. We crawled some logs, and this led to validation failures for people. So that was really stupid. They fixed that at the end of 2016, and that's why this huge drop occurs at the end of the graph. And then there's also a small minority of domains that have signed some records, but then the signature over the DNS key set is missing, and that basically also means you break stuff. Actually broken signatures, so signatures that are either expired or in some way invalid, so we can't validate them because the content of the signature is somehow incorrect, are very, very rare. Expired signatures, less than 0.6% of all signatures were expired at any given point in time, and invalid signatures are extremely rare. And the other thing that we found that was rare, which we expected to see quite a lot, but actually didn't occur so much, was mismatches between the parent zone, so com.net.org, and the child, where there would be a secure delegation, but the secure delegation would not match the key, or there would be a secure delegation, but the zone turned out to be unsigned. And that's actually also very rare. So that's good news, because it means that at least people are not breaking that. Now, we also looked at the ccTLDs because they have such large DNSSEC deployments, right? 50% of their domains are signed. And we did the other checks that I showed you before, and the situation is much the same. So if zones are signed, they're usually signed well. In the ccTLDs, the number of missing secure delegations is much lower because you only get in the financial incentive if you have a fully working DNSSEC deployment. So what we wanted to check there is if they deploy DNSSEC, do they follow best practices? And we took the NIST guidelines for that as a starting point, and the guidelines are up here on the slide, and things that we looked like was, do they use the right key size? Do they use one of the recommended algorithms? And more importantly, do they perform key rollovers if the guidelines say that you should do so at a certain frequency? Tracking key rollover, I'm not going to explain the picture in detail because I don't think there's time for that, but tracking key rollover turned out to be pretty tricky, and because you actually have to look at all of the keys that you have in your data set and see which ones changed, but this is not one day to the next it changes. Keys are used simultaneously, so you really need to work out when a key is discontinued to compute what the lifetime of that key was. And I had a student do that. His master's thesis has most of the explanation in it, and it's cited in one of the papers. Now, this might be a little bit hard to read on that screen, but on the left-hand side, you see .nl, on the right-hand side, you see .se, and listed on this slide are the top DNS operators that are responsible for 80% of the signed domains in those two ccTLDs. And the takeaway from this slide is that for algorithm choice and KSK size choice, so size of the key signing key, most operators do well. So at the top left in .nl, you see one operator that has a few red crosses for algorithm choice, and that's because they use RSA SHA-1, which NIST does not recommend that you use because it has a SHA-1 algorithm in it. It's debatable whether that is insecure or not, but that's just what the best practice states. More importantly, if you look at zone signing key size, you see a whole line of little triangles with exclamation marks in them. And that means that ZSK size would be okay if the key is rolled regularly. Because all of these operators are using 1024-bit zone signing keys. And in the next column, you see whether they actually do a rollover, and there you see red X's all across the board. So people are using 1024-bit keys, and they're never rolling them. And actually, the oldest keys that are in use have been in use for over 2 years, and they've never been changed. So that means that while these ccTLDs really have a high uptake of DNSSEC deployment, nobody is following best practices, and you can debate whether using 1024-bit keys and never changing them is really a good practice. So to conclude, while DNSSEC deployment generally remains low, there are exceptions among the ccTLDs, and there are other ccTLDs other than .nl and .se that have good results. I think, for instance, in Norway, there are over 50% of the zones are signed. Real mistakes where people break stuff, so signatures missing or invalid signatures or expired signatures, are actually extremely rare, which is good news because that means that people are at least automating that properly. But Other important best practices are seldomly followed. So regular key rollovers for weak keys, they simply do not occur. Now, one thing that you don't see in the graphs yet is that there is an increasing uptake of elliptic curve signing algorithms. I didn't have time to make a graph for that, but there is uptake of that. And that is slightly changing the picture. Is that a hint?
Yeah. And you got it.
So finally, the financial incentives that the CCTLDs have seemed to work, right? They get really high uptake of the DNSSEC. But we think that those incentives should really include mandatory quality requirements, right? You only get the incentive if you follow best practices, and otherwise you don't do that. And we talked to both the folks at .nl and .tc, and the good news is both of them are considering updating their incentives. And hopefully that will not just change the picture in their TLDs, but also in other TLDs that have signed domains as a side effect of these incentives. That's it.
All right. Thanks so much, Roland. I do apologize for having to interrupt you, but we've got a heck of a lot of things on there, and I really appreciate you squeezing into the time slot, and you got it right on the money. Is there anyone in here who hasn't seen the, oh, I'm sorry. Yeah. If you haven't seen the attendance sheets, please raise your hand and we can run it over by you. Next up, we're going to switch to another update.
I don't think there are questions, but we would have time for one question.
Okay.
No, good.
Next up, we'll have Tommy Pauly give us an update on, he visited us, I think, last year, possibly the year before, with some V6 measurements from their vantage point and Apple equipment.
Right. Hello, I'm Tommy Pauly from Apple. We've previously spoken to Maprg about measurements we've done for V6 adoption rates that we've seen from the client. We've also done some presentations about how we see happy eyeballs working of when we have both V4 and V6, how often are the races favoring V6 over V4. One of the comments that had previously come up was that we didn't have quite as much RTT data, actual performance of how V6 is doing compared to V4, and so we wanted to rectify that, so we added more to our measurements. So I just wanted to share that with everyone today. Thank you. Haha. All right, so what is new in the data that we have now? So previously, we actually had presented some RTT data about the TCP connection establishment time latency, but we weren't gathering essentially the performance of the connections overall once they ended up connecting over V4 or V6. So the new data is actually tracking the smooth RTT values over the lifetime of an entire TCP connection up until the point where the application closes the socket, essentially. And the data that I'm going to be presenting here was collected over the course of 1 month. That was just February of 2018. And it's a random sample of 0.1% of all connections that have opted into doing metrics collections. So first, just overall to give an update on where we're seeing IPv6 availability on networks from the client side. So this percentage shows the number of times in which a client device is on a network that seems to offer V6, that it even has a chance of connecting to a dual stack or V6 only host. So globally, we see 29% of the Wi-Fi networks we connect to offer V6, 44% of the cell networks do. In the US, we see that figure go up for both cases. 39% of Wi-Fi networks do offer V6, and quite nice 87% of all cellular network connectivity does offer V6. Just because we are in London, I also grabbed the data to share for the UK. Wi-Fi is at a pretty decent 32%, and cellular is completely abysmal at barely measurable, but at 0.12%. So let's work on that. So the rest of the data I'm going to be presenting kind of in this format. So to look at how we're reading this, the pie chart is just saying for this sampling, what percentage of the connections we're actually using V6. So globally, we're seeing about 13% of the connections that we're making are actually using V6. This is overall, including all networks. The solid lines are a CDF of what we see for the overall connection smooth RTT. And the dotted lines that are tracking those are what we see for just the handshake latency time. So we're comparing when we're measuring for happy eyeballs, how long it takes to actually bring up the connection, how well does that translate into the connection actually being faster overall? So the story for V6 here is really quite good overall. We do see that the CDF has a nice little bump for V6, so that on the whole, there are a lot more faster V6 connections. And we see that in general, across all networks, the handshake is a good predictor of the actual connection RTT time. But when we break it down, there are some interesting observations we can make. So here is the data for US Wi-Fi values. So here we see 14% of connections are using V6, slightly higher than the global average. Again, the V6 performance looks quite good overall. One of the interesting things we noted is that in this case on Wi-Fi, the TCP handshake latency is generally a little bit slower than what we end up with on the actual RTT. The best guesses we have, we've discussed this with several people, would be that oftentimes the handshake may correlate to when you're having to bring up the radio, and so there are more things that you're needing to bring up at the beginning of the connection that could impact its overall latency. But in general, it looks quite good. Now, when we take a look at that same chart for cellular connections in the US, we actually see a quite different story. So first of all, we have a lot more V6 connections, which is great. We have 40% of all connections in the US being made over cellular using V6. However, when we look across all the carriers, we are seeing that the observed RTT for V6 is actually trending slower than V4. And we also see an interesting thing that the handshakes are actually often quite a bit faster. This was a bit surprising, a bit odd. We looked closer at the data, and we recognized that actually one of the carriers in the US was actually accounting for a lot of the difference here. And so when we removed just one of the carrier values, we actually see that the trend shows this, in which we have V6 being, again, better performance overall, but we still see the fact that the handshakes are generally faster than the overall connection RTT. So this is a very interesting point. I'd be curious to hear anyone's thoughts on this. Our best guess at this point is that in the case in which we see certain carriers being slower for V6, if you actually go back and forth between these, you see that the main difference is that V4 was made a lot faster. And so this is probably artificially being done by essentially TCP being terminated somewhere closer to the device and actually not doing real end-to-end TCP, so that the values are being skewed. But that seems to not be done for V6 in the same way, or at least if it is being done, it's not having the same beneficial effects. So we'd love to see that be improved in the future. As far as why the handshakes are on cell often faster than the connection, which is the opposite of Wi-Fi, some of the speculations could be that although there is still a radio bring-up time that we have to worry about, the cell radio technologies may involve more batching of delivery such that the large connections would actually be slowed down slightly. So just because we're in London, let's look at the UK as well. Over Wi-Fi, we have 11% using V6. The performance actually quite good. Interesting curve for the V4 numbers here. Don't quite understand that. But we do see the same trend that we saw in the US, and we do see this actually kind of globally, that over Wi-Fi, we do expect that the handshake is going to be slightly slower than the overall observed RTT. And then just to make us sad, here's the cellular RTT values. Again, there's almost no data for the V6 on cell here. One thing I will point out is that for both V6 and V4, we see the same trend over cellular that we saw in the US, of the handshakes being faster than the overall RTT, even when we have so tragically little data for V6 here.
And I'll leave it to you, Tommy, if you want to take a quick question during the session. Or
Sure. These are my last slides, so I'll just kind of summarize and then we can go to the comments. So essentially the observations are, we see on Wi-Fi, generally we have better handshake, slower handshake RTTs than we do for the full connection. It's reversed on cell. In general, the RTTs for cell is better. For V6 is better all across the board. Cell is worse for some carriers that seem to be doing proxying. And the UK cellular network has very little V6 adoption. So, yeah. Okay. Turn it on.
Yeah, there must be a switch. Thanks, Tim.
Yeah, so I'm a bit, where are you getting your cellular measurements for the UK position? I'm just curious.
So this is just sampling from Apple devices. So this would be essentially iPhones and stuff.
Okay.
So there certainly may be other devices that have been configured differently, but at least this is the view that we have of UK carriers.
Okay, so I believe EE, maybe there's someone in the room, have about 1 million handsets with V6, but maybe not on Apple devices.
Sounds like it.
Okay.
So Tommy, do you have the order of number of measurements you have? Is like 10 or a couple thousand?
So in general, the measurements that we have for all of these are quite high.
No, I mean like
Millions,
for this
but for
IPv6,
this
yeah.
particular V6, this is order of just thousands of connections. So very, 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 very little.
Okay, let's cut the line now and let's try to do this quickly.
Lorenzo Coliti, I think eyeballing the graphs and the pie charts, I get the impression that pretty much across the board, the V6 percentage is that you end up using V6 half the time of the total connections, right? Let's say you say in the US, I think the number is 32%.
Yeah.
You use V6 about half of that.
Right, which would mainly, based on our Happy Eyeballs data, that would mainly be from hosts that are not dual stacked.
Right, but like, I guess the question is, if you used, let's say that you had a large head start for V6, how would those numbers change?
So when we look at our Happy Eyeballs data, when we have V6 available on the network and we have a dual stack host, we are using V6 95% of the time.
Okay, so maybe I'm just misreading your graphs.
Sure.
So if you go to the Wi-Fi one, like the one before this,
yeah.
Right. So I remember from the other graph that V6 and 32% of Wi-Fi of US Wi-Fi had.
Right, 39.
Yeah. So
yeah.
why is it being used only 14% of the time?
I'm imagining that's because a lot of our connections are to things that don't have dual stacked servers.
Oh, right.
Right.
Okay, so it's about, so that 50% is the content factor then. It's multiplying down.
Yeah.
Thanks.
That's correct.
Michael took some clarification question. What is the RTT of a TCP connection? I do understand what the RTT measurement for the header is, for the handshake is, but is the SRTT at the end of the TCP connection, or?
This is kind of like the smooth average that it sees for its lifetime, that essentially the socket layer is calculating that.
So at the end, you call TCP info and get that out.
Right, at the end of the connection, we look at essentially the smooth average of what TCP saw for the lifetime of that connection.
Yep. Okay. Thank you.
Yeah. Hey, Jeff.
Hi. I'm having a slightly hard time actually interpreting these profiles because what is going on is that you're not measuring V4 and V6 to the same endpoint.
That's correct.
Exactly. So what you are measuring is Happy Eyeball selected 6, and here's a profile of what happened as a result, and Happy Eyeball selected 4, and here's a profile, or the server was V4 only.
That's correct. That's correct. So yes, lots of biases in here.
Right. So I'm just sort of trying to understand that profile that you get and what is the precise meaning of the differences in the profile. Because I get certainly a wildly different answer when I look at the one endpoint and look at V4 and V6 to the same endpoint, dual stack endpoint deeper in the network. So in this profile, as I said, I'm still trying to wrap my head around exactly what you're measuring.
Right.
Does Happy Eyeballs, if you change the timers, would you change that profile? I'm like, are you measuring the V4 when the V6 is kind of okay to within 300 milliseconds or whatever time you're using?
Right. So I think it's important to consider that because we're including all V4 connections here, a lot of these are ones that weren't even eligible for Happy Eyeballs.
Right.
So it's just trying to get the overall picture.
But the V6,
Yes.
considering that there are very few 6-only sites, are V6 sites where Happy Eyeballs the race for V6 one?
That's correct. And we are often favoring that,
Oranges, mandarins, yeah? Okay, cool.
Yep.
Okay. Thanks so much, Tommy, for bringing that to us. All right, next up is my colleague Eric Nygren talking to us about an update on TLS, SNI, and IPv6 usage by clients on the web.
Hi, excuse me. Hello, my name is Eric Nygren, and I'm going to be talking a little about some measurements we've been doing on both TLS, SNI, and IPv6 client adoption. One of the main motivations for why I've been looking at this is looking at HTTPS growth, where when we have HTTPS growing rapidly, yay, but without TLS, SNI, you have no IP multi-tenancy. So the client in the handshake, if it doesn't actually send a TLS SNI, the only way the server would know which certificate to serve back would be based upon IP addresses. But IPv4 is exhausted at the RIRs, and IPv6 still has a ways to go. And if you went back a few years, TLS SNI adoption wasn't high enough to be a good general solution. However, there's been a lot of movement at TLS SNI adoption recently, making it much more viable than it used to be. So we look at HTTPS growth, even on the certificate side. This graph comes from Let's Encrypt. And you see that Let's Encrypt now has about 50 million active certificates. And if you were to try to have an IPv4 address per certificate to do this without TLS-NI, that would be about 3/8 worth of IPv4 addresses even now, just for this one use case. So that's not going to be, that's going forwards, just using IPv4 addresses to demux isn't going to be at all viable. If you also look at HTTPS growth in Akamai, even in the past 3 years, we've seen a lot of growth of customers going and taking sites that used to be HTTP only and moving them over to HTTPS, where if you went back into mid-2015, we had around 37-38% of customer host names that were delivering over 100 million HTTP requests per day were using their own TLS certificates with their own names on them, to now when that's somewhere around the 57-58% range. And if you add on top of this customers using wildcard certs, and you also kind of mix in the fact that some of these host names do have a mix of HTTP and HTTPS traffic, we're seeing around 75% of requests we serve now are over HTTPS, which is a huge improvement over what it was a few years ago. If we look at TLS SNI, if you even go back a few years ago to 2014, the SNI story was pretty bleak. This is the percentage of requests that would come in to Akamai over HTTPS that sent TLS SNI. And back in 2014, that was in that 80 to 85% range, which is something where if you go to a customer and you say, hey, go turn on HTTPS, but be SNI only, it only break 15 to 20% of your end users, that's just not going to fly so well. But if you go back to even where we were at the start of last year, in 2017, that was starting to get up into that 98% range, and still 2% is in that there are a lot of large sites that will not be, who may have a 3 or 4 nines availability goal. We're telling them, hey, we'll only break 2% of your end users. Is still not great, but it's still a lot better than the 15 to 20% that it used to be. But if we now look at where it is in the past and how this has changed in the past year or so, even in the past year, we've seen substantial improvements in terms of clients that are sending TLS SNI as some of the remaining things that have gotten fixed. So this is showing here a CDF across Akamai customers or Akamai customer certificate slots, which and for just the HTTPS requests on those with customer certificate slots, and bucketing them by what percentage of HTTPS requests came in that sent TLS SNI. And if and each of the curves is a CDF at a different point in time. So the yellow one is from February of this year, And then you look at that, and we're now at that point where 31% of customer configurations of slots have SNI adoption that's over 99.9%. So, and if you look even at the median is starting to get into that case where, and I'll talk more about the median later, the median's also well over 99%. However, there are still plenty of customers we see who have SNI usage that are still low. So for example, 21% of our customer configurations have SNI usage below 97%. And a lot of that is because people will have custom apps, custom devices, custom appliances going and doing HTTPS, but not sending SNI. So if you go back and look at some studies that were done a few years ago, for example, Cloudflare had one. It showed a big variation in the global median. So we'd see some countries like China that had much lower SNI adoption than others. If we go and look at that now, we'll see that that globally it's actually leveled out. A lot of that global variation between between countries has settled out. So for us, we see our median customer usage has around 99.7% of HTTPS requests sending TLS SNI on their TLS handshake in almost all countries and geo regions. Globally, that median's around 99.76%. But however, there are a lot of countries around the world where that median has gone over 99.9. And the lowest that we'd seen even kind of middle of last year was China. And it turned out that a lot of that lower SNI that was remaining in China was due to one search engine, and having a conversation with them, they started sending TLS SNI and pulled China's median back up to be similar to the rest of the world, at least from our perspective. And if you compare this over to TLS 1.2, there's actually less usage of TLS 1.2 than there is of TLS SNI. And there's not always a strong correlation here. There are a lot of TLS 1.0 clients that do send SNI and some TLS 1.2 clients that don't. But SNI usage is actually ahead of where TLS 1.2 is. So for people who are at this point considering turning off TLS 1.1 and 1.0, that's going to be more impactful than switching to something that is SNI only and requires SNI to work.
You got about 3 minutes. 3 minutes.
Okay. I thought it was 15. So what doesn't send TLS SNI? There's a lot of what we're seeing, we see custom clients and apps, gaming consoles, antivirus things. There are things that have spoofed user agents or man-in-the-middle devices like antivirus and secure web gateways. Windows XP used to be the thing that was the bugaboo, but of the non-TLS SNI traffic, only about 6% of that is not sending SNI, and also older versions of Python, Java, and Apache Client are also around 4% of the non-SNI hits we have. And there used to be a big issue where even last year, a lot of search bots didn't send SNI, but all but one in China have fixed that now. But then there's a long tail of other things, and anecdotally, some of that's getting fixed. Like I found Apache Bench on there as one thing that didn't, but there are commits in the non-released version that add SNI support.
Eric, you were right. You have 7 more minutes.
Okay. Now I'm a little less panicked.
I looked at our own agenda.
Okay. So for IPv6 trends, the methodology we're looking at here is looking at 24-hour snapshots of data. It's the same data that we've been sending to ISOCs for worldipv6launch.org for the past few years. And we're looking there at a few 100 billion HTTPS requests across dual stack sites and looking for what percentage of those requests are over IPv6 relative to the total hits. And I've been focusing in the past on what are the top IPv6 leaders here, but as we start getting that global average in IPv6 moving up, depending upon what the mix of content is, we can see that global average being anywhere in the 17% to 31% range. And you'll see outliers like websites that are heavily mobile may see something closer to 31%. as their global average. You may see some enterprise software downloads that are only a few percent IPv6. But if we look at how do we get that global average to keep moving, how do we get it to not stall out at 50%? I've started looking at what are the top areas with residual IPv4. What are the things that we can do the most work to get that residual IPv4 to go away? And there tend to be two clusters there. There are places where IPv6 deployments are already in progress, and then there are places where there's little to no IPv6 yet. And both of those are areas which may have different strategies for what can help move the needle in IPv6. And a lot of this ends up being heavily influenced both by the content and ISP networks that are deployed v6, but there is a lot of content mix sensitivity here, as I mentioned earlier. So if we look at what are the top countries with residual IPv6, and that breaks down into two buckets. So those countries that already have IPv6 deployment in progress, but where there's still a lot of opportunity, and those are actually the top ones, at least from what we're observing, and everyone will observe different slices, but from our observations, the top opportunities for residual IPv4 are in those countries that are already moving on IPv6. So US is at the top of the list, already at 41% IPv6 by hits. But below that you have the UK and Japan and Germany and India, which are also already deploying v6. But then you go over to the other side, there's a set of countries that are further down the list. None of them are in that top 10 of residual v4, but they have less than 3% IPv6. In some cases, it's close to zero when observed globally. And those are Russia, China, Italy, Spain, Indonesia, Turkey, and South Korea up at the top of that list. And there are a few of those that may have IPv6 in country, but their IPv6 connectivity or peering to the rest of the world is sufficiently bad that it's hard to actually measure it, and that Happy Eyeballs is flipping over to not use v6, and therefore it looks low. So on the device side, on the high side, there's a lot of the modern devices do IPv6 well and use it quite a bit of the time. Oddly, there's the IPv6 preference across the board we see for older versions of Windows seem lower. That might be because it is a heavier enterprise deployment or heavier deployment in some countries. But there's a lot of opportunity on the very limited IPv6 side among especially set-top boxes and some streaming set-top boxes and some custom apps. If you look at that, there are some vendors of consumer electronics and set-top boxes that do v6 and have averages in that 30-ish% category, but then there are others that are 0% that are actually fairly high in the residual IPv4 bucket. The same goes for custom applications where people may have written some app and just don't send v6 from it. If we look at things on the network side, one of the things is and one of the questions that comes up in some discussion forums is how do we not get IPv6 stuck at 50-ish%? And when looking at what that distribution of networks is like, it's not just the big networks that we can solve the problem with by themselves. Like if you look at the top 55 networks by residual IPv4, there's about top 55 networks account for half of the residual IPv4, and over half of those have IPv6 greater than 2%. So in that front end of networks, you have a lot that have started deploying v6 already. But if you want to get out and handle the next 50% of residual IPv4 traffic, that's going to require networks that haven't been deploying v6 to start deploying it. So if you want to get out to the 90th percentile of residual IPv4, that's going to take, there's 1,200 networks there, and only around 18% of those have IPv6 greater than 2%. But one thing that is a positive sign is there are a lot of networks out there that have v6 configured, but haven't actually turned it on for their end user eyeballs. So for example, our networks team has been able to get v6 working on servers in around 840 networks and 114 countries around the world, which is significantly more than you necessarily are seeing high IPv6 eyeball usage from. So that's it. There's the links have some more stats. There are also on the support slide some graphs on various networks and countries.
Thanks, Eric. Question or comment? Okay. So next up, we invited Jan Ruth to come and talk to us about two different topics that they've been studying lately, both active measurements in the V4 space.
We just recently got V6, so.
You mean the university?
Yeah.
Yeah. Okay, take it away, Jan. You got 25 minutes total, and you get to decide between your two presentations how much you want to spend on each.
Okay, so this is work we've been presenting at IMC last year and some new stuff that hasn't been published yet. So basically this is about TCP initial congestion window. So why would you actually bother? So basically TCP's initial window is the amount of bytes that you're allowed to send in the first round trip of a new connection. So it basically bootstraps the congestion window and slow start. So with every round trip, you will effectively double your congestion window. So which will lead to, as you can see in the plot on the left, your congestion window will ramp up faster. And if you take a closer look at some performance measurements, you'll see that you can actually have faster flow completion time, for example. So you might think, well, this is nice. So why aren't we just making it very large? So, well, because at the start of the connection, you have actually no clue about your network. So you'll be bursting, or at least the standard TCP will burst the initial window in an unprobed network. So you only know one sample of the RTT at start. Well, and as it turns out, depending on the available queue sizes that are in your bottleneck link, this will lead to a lot of losses. So you will have a lot of retransmissions, which isn't good. So the question is basically, what is it? What is the initial window? So, well, good thing we have standards for that. If you take a look at the standards, you'll see that, well, there are various things in the standard. So at the start, there wasn't really a lot of congestion control. Only in 88, Van Jacobson proposed, well, use an initial window of 1. This was then standardized. Then there was an experimental standard that said, yeah, use 2 to 4. Then people started measuring it. Then it was actually standardized. And most recent standard says, well, you can use an initial window of 10 segments. And this is also already in the Linux kernel since 2011. But basically what I would say, yeah, we don't know because, well, do people actually follow the standards? So what we try to do is to figure out how that looks like in IPv4. To do so, we actually wanted to contact all available IPv4 hosts. And so the question is actually, how would you measure the initial window? And we do that in the following manner. So on the left is our scanner. On the right is the host that we are going to probe. And what we are going to do is we are establishing a regular TCP connection by doing a 3-way handshake, but we're announcing a very small segment size because in many implementations, the initial window is a multiple of the segment size, so we won't need a lot of data later on. And we'll be announcing a very large receive window for the flow control because effectively, a TCP will send the minimum of both the congestion window and the flow control window. And to be never limited by flow control, we just announce a very large one. Well, after we've done the 3-way handshake, we'll send a request to that host in hope to trigger a lot of data in response. When the host will start sending segments, we won't acknowledge any of those because when we acknowledge them, it will effectively increase the congestion window, which we don't want to do. So we'll just not acknowledge anything. And after a certain time, the host will stop sending any more frames because it's just the initial window is full. And we'll have a timeout and a retransmission of, for example, the first segment. At that point, we can actually start establishing the initial window by observing the sequence number space of the packets that we got. However, you might see that there are some problems in doing this. For example, what happens if some segments are lost? And this is especially problematic if the last segment is lost because we can't detect that. So what we actually do is we just scan multiple times and hope that over 10 scans, we won't have a lot of tail loss. And what you should also do is you shouldn't enable sec so that there are no tail loss probes or something like that. But there are also other problems when you do it because how would you actually know that, for example, that end segments were actually the initial window and maybe the host just did only have enough data for end segments. So the next thing that we actually do is we start acknowledging data. And if more data is coming, then we actually know that the other end wasn't application limited, but was in fact limited by the initial window. So we basically implemented that in ZMap to scan all of IPv4 on with HTTP requests and with TLS client hellos. And well, when you do this, the following picture appears. As you can see, all of IPv4 is basically dominated by 4 values. That is initial window of 1, 2, 4, and 10. The first thing that you're probably noticing is that TLS and HTTP distributions do not agree. There are more hosts using TLS on an initial window of 4 than compared to HTTP, where you're seeing more on 10. As it turns out, after we ran these scans, our inboxes ran over because people were complaining that our scanner were appearing in the access logs. This funnily only happens with HTTP, not with TLS, because people don't log that for some reason. So we actually took a look at, do we actually need to scan all of IPv4 to derive these values? And well, as it turns out, for at least our measurement, it was enough to scan 1% of IPv4 to get the same distribution. Well, now you might say, okay, it's a performance parameter. Why would I care how some host in IPv4 is configured? So let's look at the services we're actually connecting to. If you take a look at the Alexa list of popular domains, so here now the plot is with a logarithmic scale, so don't be confused. You can still see that 2, 4, and 10 are present, but now the share of 10 is a lot higher. So it's around 80 to 85% depending on HTTP and TLS. And you can also see that both distributions start to agree at least on the RFC recommended values. You can also see that there are some custom or larger values. Generally, we saw that actually these initial windows that were standardized a couple of decades ago are actually present in access networks. And if you connect to these IPs manually, you'll see, well, this is some gateway in some ISP or something. But the next thing we were asking us, okay, how does it actually look with the infrastructures that we're contacting the most if we are getting data today? And so we took a look at content delivery networks. And to do so, we used the HTTP archive and got a lot of lists of URLs that are hosted on CDNs. And as we have now a lot of data and we know about that, we can use regular size segment sizes. And we use, again, HTTP and also a window scaling option because, well, some of them send a lot of data in the initial window. So what you can see here basically is an overview of what we got. So I anonymize the CDNs. Basically, the blue box on the lower left is what the current standard says. And as you can see, for example, CDN B has a 10 times higher window than the current standard. However, most of the CDNs are below an initial window of 50. Further, you can see that if you take a closer look, there are some CDNs in there that actually customize the initial window depending on which customer or what services they're actually using. So there are some that use 16, and there's for other customers, they use 32, for example. Okay. This brings me to my last slide of this talk. So what you basically saw is that the distributions are generally dominated by the RFC recommended values. There's still a lot of initial window 2 and 4 in the whole of IPv4. Popular hosts seem to have updated to initial window 10. We also find some customization. We find some very large initial windows. And it seems that CDNs are far beyond current standards. And when you look more closely on this, you can even see that some customize depending on the access network that you're using to contact these hosts. You can get data on our website, and yeah, well, I'm happy to take questions.
Hi there. There was a presentation 2 IETFs ago about, it was actually about measuring ECN, but it also incidentally measured IW10 and it got very similar results, but didn't go into as much detail as you. However, it did also measure from about 50% of its vantage points on mobile networks, and I think all yours is fixed, isn't it?
Yeah, this is all fixed, so from our university network.
So the data's available. I can post the URL on the list. Sure. and all the rest of it, and the papers and things if you want to compare.
Thanks.
Okay, let's take the one more.
Stephen Strauss, right, CC. I will be looking forward to your IPv6 results. And part of the reason I'm asking that question.
Well, IPv6 enumeration is a bit tricky.
Sure. Like we can talk about scanning the v6 space, but since you're talking specifically about CDNs, a bunch of the CDNs do pretty aggressive MSS clamping, and I'm wondering how that affects your results. That's why I asked the question. A bunch of the CDNs do fairly aggressive MSS clamping, so I would be interested to see how that affects your results.
Yeah, well, so we further looked at the CDNs, and we were wondering how they were actually delivering the initial window. And well, we looked at them, and some of them seem to paste their data, not all. But yeah.
Okay, so I'm going to pull up your next presentation, which is a first look at Quick in the wild. And I think we've got 20 minutes total, including questions. So maybe 15 minutes you got.
Well, so I just start. So basically, we would only be presenting this next week at the PAM conference, but as I'm here today, I thought it might be of interest to all of you because Quick is the hot thing right now. Yeah, so this is joint work with colleagues from Banox and TU Berlin. And well, I don't need to tell you how awesome Quick is because you all know that. Basically, there's Google Quick currently out there, and you're standardizing the other version. And we were asking ourselves how much Google Quick is actually out there. To answer this question, we basically want to answer these three questions. So what infrastructures are actually out there supporting Quick? Is it practically used by any website today? And how much traffic is Quick today in the internet? To tackle the questions, yeah, we again look at IPv4 and perform ZMAP scans. Further, we also look in zone files of the .com, .net, and .org zone, as well as on this Alexa list. And further, we take a look into traffic shares in a university network in a major European tier 1, in its mobile network, as well as in an IXP. I'll start with the first question. So, well, to the foundation of that question is basically how are you going to find Quick capable servers in the internet? And luckily for us, Quick has a version negotiation feature, so to be evolvable in the future. And it basically worked like this. So a client sends in a first packet in the client hello or in the initial in IETF Quick its version. And if the server supports it, it continues the handshake. However, if it doesn't, it will send a version negotiation packet, and that version negotiation packet will include a list of versions that the server supports. So what we basically did is we wrote a ZMAP module that tests for that. So we'll send a valid client hello packet. However, we are going to include a version that is very unlikely to be supported by the other end. So if the server doesn't support that version, he should, if he's implemented correctly, send a version negotiation packet. So we can, from the packet structure, deduce that the end host is capable of doing Quick, and further we also get a picture of the version that it actually supports. Well, so we've been doing these observations in IPv4 since August 2016. And I'm going to show you now data that covers roughly a bit more than a year, so until October last year. So what you can see is starting from August 2016 to 1 year later, you can see that the number of Quick capable IPs more than tripled to roughly 600,000 IPs. As I said, Quick is now versionized, so we can further take a look at which versions were supported when and how vibrant all this Quick landscape actually is. And if you color the plot depending on the versions that the host actually announced, you'll get the following picture. So basically what you can see is that it's very colorful, and furthermore that there are some versions that fade away over the time, but if you take a very close look, you will see that they're actually versions that are quite stable all over the period that we observed. So for example, version 35 was available in August and is still available in October of last year. Yet, given the colorfulness and a lot of changes, the question is, how will a future quick internet actually look like? How often will we change versions? And as you all know, updating systems in the internet tends to be quite challenging. So the question would be, if versions are deprecated, if you'll be creating islands in the internet of versions of Quick that, well, you wouldn't be talking today anymore. So the next question is that we ask ourselves, who's actually operating these IPs? To answer the question, we took a look at the ASs in which these IPs are hosted, at certificate data and at reverse DNS entries. And what you'll find is that for roughly 53% of the IPs, you can attribute them to Google. Well, that's not a large surprise, I guess. For the rest, as of October last year, we were able to attribute them to Akamai. And you can actually also see that the growth that you see in that plot is due to Akamai. So in August of 2016, they only roughly had 1,000 visible IPs to us. And as of October, as of November the same year, it's already 44,000, and then it continues to rise. So that still leaves us with around 6 to 7% of hosts that we couldn't classify that way. So we did HTTP requests via TCP to find out what the remaining ones are. And first thing that we noticed, we get many timeouts. So they're hosts that are exclusively running Quick. Further, we found more Akamai and Google servers that we couldn't attribute using the classification from above. And we also found roughly 7,000 Lightspeed web servers. And this is a web server that announced or included Quick support in August last year. And also roughly 350 Caddy web servers, which is a web server that's based on the Quick Go library. Well, if you're interested to see how that continues to evolve, you can check out our website, and there's more data, and we also publish all the data on a weekly basis. Yes, so this continues. Well, now we have infrastructure. So is that infrastructure actually used by websites? To investigate, we look at the .com and .net and .org zone, which roughly contains 150 million domains. And unluckily for us, there are no tools out there to actually investigate Quick usage. So we had to build some that are efficient enough to look at this number of hosts. And we built them on top of the Quick Go library I just mentioned. And we modified it slightly so that we can basically trace the handshake in a very fine-grained manner to dump all the connection parameters that are actually established when you're doing a Quick connection. You can also get that. Well, basically now we have an efficient scanner for these domain lists, and we can then further analyze the connection parameters. So for example, do these hosts actually deliver valid certificates for the domains that we are requesting? Again, this is data as of October last year. This is just for completeness, so let's focus on some of the data. So from all these 150 million domains, you'll basically see that there are 160,000 domains that are hosted on Quick-capable infrastructure. And, well, today, when you would visit them with your browser, a lot of them wouldn't work because they don't offer valid certificates for these domains. So roughly only 3,000 valid certificates were given to us. And, well, for example, if you have a Chrome browser, it works like this. You will be first visiting the HTTP or HTTPS variant of the website via TCP. And if you find a certain header in the HTTP header, that will tell you that this host actually also supports Quick and you will be using it. However, even for the valid certificates, we only found a very small fraction that actually announced this header. So in practice, you wouldn't really be using probably a lot of these hosts using Quick today, or as of October. So the next question basically is, given that there's, well, not a lot of practical Quick out there, how much Quick traffic is there in the internet? To answer this question, we have to get a step back. So how do we classify Quick traffic? Classifying Quick traffic is a bit hard because everything's encrypted. And Yeah, I mean, you're just seeing garbage. Apart from some packet numbers or something. So we basically relied on the port-based classification. So everything that we saw is basically on UDP port 443. That's quick. And we are going to classify that as quick, which will give us an upper bound on the quick usage. So that might be a bit lower. The same TCP port for HTTPS and port 80 for HTTP. And depending on the data source that I'll be showing you, we have AS level information available to see who's actually calling that traffic. Okay, we start with the so-called Mavi trace, which is an open data set, which basically provides 15 minutes each day at 14 o'clock of capped packets. And the source and destination have been anonymized. However, we can still analyze them, and this is what you get when you do that for the first 10 months of last year. And what you will see is here in blue, quick, in red, HTTPS, and in yellow, HTTP. And what you can see is that there's no quick traffic as of January last year, even though we found that Google said, well, we activated it in January for most customers. So these don't seem to be most customers. But as of March, we already see on average 4% of quick traffic, and as of September, roughly 7%. Yes, as this is an open data set, we can continue doing so. So there's more data, again, on the website. And if you look closer into that small picture, you will hopefully see that it still continues to rise, and there are some peaks around 30% of quick traffic in that trace. Okay, that still doesn't answer the question who's calling that. And for that, we took a look in a major European ISP. And we were basically lucky to get anonymized let flows of all of their border routers. And we got them for one full day in August of last year. And it basically contains all of their upstream and downstream traffic, so including their edge customers, their cellular customers, and the backbone traffic. And the IPs in that trace have been replaced by the AS numbers for us. And here you can already see the daily pattern. And what you can see now, again, the same coloring as before. However, we hatched the plot depending on who caused that traffic. So we saw that Akamai and Google have capable infrastructure, so we specifically looked for those two. If we take a closer look, so here on the left is a relative plot of this. What you can basically see is there's quite a stable quick share all over the day, and it is roughly at 7.8%, plus minus 1 all over the day. Further, HTTP and HTTPS are still dominating with roughly 40% each. And most of the traffic that we see, so if that's large enough, I can improve, you'll see stars in that plot, and that means it's Google traffic, or it's coming from or to Google. In fact, actually, Google is capable of pushing up to 42% of their own traffic with Quick, which averages at roughly 39%. But we see close to no Akamai traffic in that trace, so 0.1%. Still, if you take a look at the HTTP and HTTPS traffic, Akamai calls a lot of the traffic. So given that they have a capable infrastructure, this is potential future quick traffic. When we take a look at the mobile network of that ISP, the first thing that you probably notice is the daily pattern looks different. So people seem to be using their smartphone all over the day, starting in the morning. And you can again see that there's Quick in it, and here the Quick share is slightly larger than for the whole network. It's at around 9.1% with a slightly higher deviation. And Google, again, dominates the share. And they can push up to 34% of their own traffic with Quick in that network. To round that up, we had a look at a major European IXP, and we got the same quality of data for the same day in August. And so we got the flows annotated by the customer port, and you can basically get the same image again. The first thing that you notice is that there's a lot less blue here. So Quick is only roughly at 2.6%. Furthermore, if you would now start zooming in on that plot, you'll see that actually Akamai accounts for 60% of the Quick traffic here, and Google only for roughly 33%. Honestly, we have no real idea why this is the case. We just assume that both companies seem to have some different traffic engineering strategies, so it seems to be more valuable for Akamai to use the IXP or less valuable for Google to use it. We don't know. So to summarize, Quick is on the rise. There's a zoo of versions, which still, at least my point of view, questions future compatibility. More and more infrastructure is actually enabled, but there's only a small set of domains that actually maps to this infrastructure that can practically use it. Even though we see, so nevertheless, we see that the fraction of Google traffic is already quite high. It's very vantage point specific, and there are single companies which have quite potential to increase the Quick shares given their infrastructure. And it also challenges the question how Quick traffic actually impacts internet traffic as a whole. Okay, thank you very much. Yes.
Okay, we've got a few minutes for questions and comments if you have them. One of the things I particularly appreciated about Jan bringing this work to us is he and his research teams. One of them is from IMC last year, the initial window talk, but this is an upcoming publication next week at PAM. So you're one of the first to see it.
Yeah.
Yes.
Dmitry Tikhonov of Lightspeed. Just Lightspeed is spelled L-I-T-E.
Any other typos? All right, thanks, Jan.
So wait, in the Java, I think there was a question about the availability of the data. I guess your own measurements might be available or shareable.
Yeah, so our measurements basically are also, we cannot make available the IXP and the ISP traces, obviously. Well, the Mavi trace you can get on that website. It's not too hard to detect Quick in there. We cannot publish the TLD stuff because the lists are under an NDA, but the IPv4 stuff we publish on a weekly basis. So every Friday, I guess, the scan is running, and on Saturday, the data should be on the website.
Okay, perfect. Thank you. So next speaker is Torsten, talking about server push.
So thanks for the introduction. Yeah, so I would like to talk about the adoption, the human perception and performance of HTTP2 server push. So just a quick reminder, what are the major changes of HTTP2 in comparison to HTTP1? It's a binary representation, not an ASCII representation anymore. We should use only a single TCP connection, and we can have streams on that single TCP connection that can be multiplexed and prioritized, and we have header compression. This list is incomplete. There's flow control and other stuff going on. And there's one particular feature that caught our interest, and that is server push. And among web developers, this is often regarded as a key feature for H2. So just to give you a quick overview what push does, remember how your browser back in the old HTTP1 days requested a website. So you request the base HTML document, the browser starts parsing the document, it will detect a style sheet, it will detect a JavaScript, and then it will issue a new request to the server. So with server push, the server has the ability that upon a client request, it can push these resources to the client without an explicit request for that. So this technique then saves requests and ultimately round trips, and so this should improve the performance. So, however, the standard itself does not provide any strategy to what resources should be pushed and when they should be pushed. And moreover, in comparison to the other features offered by H2, this feature needs active configuration. So you get all the stuff on the top for free by just upgrading your server software. But server push itself has to be actively configured. And this is why we say that if you see server push in the wild, this is an indicator for true adoption to a new protocol, because this feature is actively configured. And this then motivated our study to look into who is using server push and what is pushed. So first of all, before we can look into what is being pushed, we need to identify HTTP2 capable websites. And for that, we use the Alexa 1 million list and the complete set of .com, .net, .org domains. And again, because I work at the same institute as Jan, we are huge fans of ZMAP and built an scanner for the IPv4 space. And we explicitly look for TLS and application layer protocol negotiation and its predecessor next protocol negotiation announcing HTTP2. And given these two data sets, we then utilize HTTP2 capable library, it's the ng-HTTP2 library, and try to see is actual content delivered via HTTP2. So we define this as full HTTP2 support because for some websites you see that they say, I speak HTTP2 and then you're redirected to HTTP1. So we define full HTTP2 support if the website actually delivers content via HTTP2. And we instruct the library to visit the landing page and follow up to 10 redirects. And we distribute it to multiple workers in our network and also publish this data on a regular basis on our website. So for small domain lists, we do this on a daily basis, and for the larger domain sets, we do this on a weekly basis. So to give you a quick look at the HTTP2 adoption at a glance, this is just in here for completeness. I would like you to focus on the top right now. So over the last year, from January 17 to this year's January, we see that the HTTP2 adoption on the Alexa list has doubled, which is quite nice. And the usage of server push has also increased by a large factor. However, if you have a look at the absolute numbers, out of 220,000 domains on the Alexa list, only 1,000 use server push. And we see the same on the .com.net.org set. So there also the adoption of HTTP2 has nearly doubled. We have over 11 million websites speaking HTTP2 and 5,000 websites using server push. Back in January 17, we saw that 7,000 sites were using server push. However, there were 6,500 websites registered by a domain parker. They were all using the same template. And if you take them out of the equation, you have only roughly 560 websites using server push. So given this data, we ask ourselves, so we see, okay, HTTP2 is out there, server push is out there. It's not that much used than HTTP2 itself. So who's driving the adoption there? And we do a case study for the Alexa 1 million list, and we see that out of all websites that speak HTTP2 on the Alexa 1 million list, most of them are hosted by Cloudflare. And when looking into the websites that use server push, we again see that most of them are hosted by Cloudflare. And then we see a drastic increase that we also Akamai on the list. So if you have a look at this over time, you get the following picture. On the lower left, you see what I just said. We see a rising adoption of HTTP2 on the Alexa 1 million list, and also an adoption of HTTP2 and what a server push. And I would like you to focus on two special things in the lower right plot. You see a drop in last year's September. So what happened there? So we looked into that and saw that, unfortunately, Cloudflare had to temporarily deactivate server push for their customers because a lot of customers were, for example, using WebSockets over HTTP2, and most, as you might know, this is currently not possible. So they had to take down this feature for maintenance. And if you have a look at this rise in this year's February, we see that it's also caused by Cloudflare, because it seems that a lot of users that host their website with Cloudflare use a certain content management system. And this content management system called HubSpot had recently done a software update, and they introduced preload headers. So preload is used to tell the browser, this is some content that might be you want to fetch very early because you will need it later on. But Cloudflare uses this preload header to identify what to push to the client. So we see a rising adoption here. So we next focused on how much do the websites push to the client. And this is the picture for last year. So in general, we saw nearly 600 websites utilizing push, and we see that around, for example, if you take a look at the left plot, 80% of them push 20 resources to the client. If you take a look at the share of resources plot, that are the resources that are pushable to the client, and these are the resources that are on the same origin than the landing page. We see that for some websites, they push everything they can push. And we see that the top three content types are JavaScript, style sheets, and images. And here's an updated view on that from this year. We see for the first part, not much has changed there. However, for the MIME types, we still see that JavaScript and style sheets dominate the top list, and there are less images in comparison being pushed to the client. So now that we see pushes out there, it's used, and actually there's some stuff pushed to the client. How does this impact the overall performance? Because in the beginning I said on paper, this should improve the performance. So what we did was we configured a Chrome browser to automatically repeatedly visit these websites and recorded performance metrics. First of all, we recorded the page load time, and we take the time between the connect end event and the load event start. And have you look on the left plot, there you see actually we compare the HTTP2 version of the websites using server push to the HTTP1 version, normed to the HTTP1 case. So the red line on the left is the portion of websites that improved in their page load time. And on the upper right in this plot, you see the websites that suffer from using HTTP2 with server push. And to identify if this is caused by server push, we looked into, please have a look at the right picture, where we compared the websites, their HTTP2 version without server push, because the client can deactivate this, compared to the version with server push. And again, it seems that some websites improve using server push, but some websites, although they might improve only using other HTTP2 features like stream multiplexing or header compression, they suffer from using server push. Yeah, and you can argue, okay, page load time is a very technical metric because after the onload event, there might be a lot of other stuff going on. And therefore, we also looked into the speed index. The speed index is a metric defined by Google, and it basically measures how quickly the page contents are visually populated. And I won't go into much detail here, but it draws the same picture. So we then tried to map these results to the results we saw before. So how much is pushed by the websites, what content is actually pushed, and how large the content is. But we could not attribute this to simple reasons, so to the number or share of objects. So we next ask ourselves, yeah, these are all technical metrics and we saw inconclusive results, but in the end, it's people visiting websites. So do people even notice that there is a change going on? And for that, we conducted a user study. And basically, we created an online questionnaire where users had to view side-by-side comparison of the loading process of a website. And I wanted to have a close look at the baby that looked like this. User visit the websites. They see side-by-side videos of the loading process of different versions. So the left version here is actually the HTTP1 version, and the right version is the website's version using HTTP2 with server push. And we ask the user to say which version loaded faster. And I won't go into all the details of the results here, but what we saw was there's a strong agreement among the users. So in nearly 60% of our tested scenarios, more than 75% were in favor of one version of a website. So people could clearly tell what caught their interest and what was they perceived faster. For over 36% of the websites, more than 80% said, I like the push variant more because it was faster than the AH2 variant without server push. However, for a non-negligible amount of websites, we saw that some of the users were even in favor for the version without server push. So the key takeaway here is that server push can lead to human perceivable negative performance. And after we did this questionnaire, we talked to the people and tried to identify reasons and also looking into the rendering behavior in the browser of these websites. And there are various reasons that may have caused the decision in the end. So, for example, like I said, we see that a lot of websites even benefit from other HTTP2 features like multiplex streams, which lead to less head-of-line blocking. We see that if you push too much resources for the base document, the browser is delayed in processing the base document, and thus the overall performance suffers. And we also saw some weird effects. There were some websites configured that they push resources that are not actually referenced in the website, so they are not used. But as we always use a cold connection to a server, pushing more enlarged the congestion window, and then ultimately the actual page was loaded faster. So as a takeaway here is, if you want to use server push for a website, you should really know the website, you should know how the browser behaves, and you should know how the server behaves. And I would like to, before I come to an end, quickly show you what we're currently looking into. Based on these results we saw in the technical analysis and in the user study, we are currently analyzing server push in our control testbed. So to remove the variability we have when measuring it in the internet. And we're using real websites, and we're using the Mahi tool for that. And what's cool about that is that it tries to replicate the real world website structure. So it will spawn multiple namespaces for third-party resources and for additional resources. So you're not just saving a website to a local server, it tries to replicate how the websites look in the internet. And we're testing various strategies for server push there. And some early results are you shouldn't push everything you could push on the websites. Don't push images, at least not large images. And you should just push enough to fill the initial network idle time. Because we see that after the browser received the pushed file and then the initial bytes of the HTML, most browsers, at least in our test, were fast enough to then issue old requests for resources. What we're also currently looking is into an alternative scheduler for an HTTP2 web server, and we try to push the right resources at the right time. And what we do there is that we identify resources that contribute to above default viewport, so the stuff you see if you open the website, and we try to interleave these pushes with the base HTML document. So we instruct the scheduler to just push the first bytes of the website, stop pushing the HTML, and then push resources like style sheets. And we already see that this can lead to promising results for some websites in our testbed. However, still, this depends on the overall structure of the websites, the number of third-party content, and ultimately the browser behavior. So takeaway here is, unfortunately, we cannot give you a single generic guideline for server push, as it requires website-specific tuning and configuration. And so to conclude my talk, what's cool is we see a rising adoption of HTTP2, and a lot of the features there, like the multiplex stream prioritization, can really improve your websites. And we see that every now and then there can be a drastically increase by just updating the server because all major browsers already support it. And regarding the server push feature, I still think that it's a very cool feature. However, you shouldn't just switch it on because it's no silver bullet to improve the website performance. We've seen that it can lead to human perceivable negative performance. And up to now, I would say it requires a lot of deep understanding of the page loading rendering process in the browser. So I think we should all agree on that we need best practice and guidelines for the use of server push. And with that, I would like to thank you for your attention and conclude my talk.
Thank you. So we have some time for some questions. Dave.
Yeah, I have one. Not chair related, but in the portion about analyzing the Alexa top million, when you're trying to determine who's hosting the content there, what is the strategy you're using? How do you go from the Alexa domains to site names?
Yeah, so we started off by IPs and then try to map them to ASs. And we are also doing on a regular basis DNS measurements. And there we simply try to analyze the whole DNS chain and follow the CNAMEs and identify if it's then, for example, hosted by Akamai or Microsoft or whatsoever.
Okay, so
I mean, this can be an incomplete list. I don't think we have 100% coverage there, but yeah.
Yeah, maybe I guess a hint I want to offer, not just for your study, but using passive DNS can get you the collection of fully qualified domain names underneath a domain. And what I find a lot when I'm studying it is there are very many Alexa listed services that use many CDNs simultaneously. Yeah. So I'm curious to know what subdomains they might be using server push in, or something that you wouldn't see just at the TLD.
Eric Niger and Akamai, actually follow on to Dave's. This is probably a general thing for people doing this class of measurements to think about, is that especially as more sites move to SNI, the kind of ZMAP IPv4 scan, let's go try it, is going to start becoming decreasingly useful because many things may switch their behavior based upon which SNI they see. And along with, also as the IPv6 stuff is becoming more and more relevant there, but also I think on David's one about the Alexa one is one thing you'll also see is that the Alexa very much focuses on www style sites, where there ends up being an increasing amount of content that is on separate domains for images, videos, etc., that don't show up as well on that list. I think the other question side of this is for where you're looking at the push performance behavior is you showed that there are a number of different providers who are providing push. Did you break that out by them to see if that was common across the board, or was it the case that some of those providers had behaviors that on general were negative and other ones were taking strategies that tended to be more generally positive?
So we couldn't attribute this to the provider itself. It's more like the configuration of the website. So the user hosting the website at the provider. So for example, I said in the beginning that push requires manual configuration. And but there are also some websites where we see that plugins do this configuration, like WordPress plugins. They scan your file tree and they see, hey, there are some static files. Why not push them? And so it's more like the configuration of these features than instrumenting the infrastructure to say push this and that influence the performance. Not so much the infrastructure itself.
Right, but I think there actually are starting to be a number of product features by various vendors that will go and analyze website behavior and then feed that back into the push behavior.
Yeah.
So you may see cases where that kind of closed loop analyze and decide what to push has very different characteristics of behaviors and stuff that is more statically configured.
Yeah.
Thanks, Eric.
Ian Sweat, Google. First, I want to thank you for publishing this work. I've repeatedly asked for good public evidence that push actually works well or poorly, and it's really hard to get good data, and this is as good data as I've seen. And I really thank you for that, and I think it emphasizes the challenges of making push work in the wild, which are real, and we've seen them at Google. I mean, it's possible to make it work, but it's a lot of work. The second, the actual question portion was, have you considered evaluating cache digest and whether that makes things much better?
Yeah, so we will look into that. As you might know, today at the HTTP this meeting, there will be a talk for cache digest and really looking into it because there's still a lot of stuff that can go wrong with server push. And it's still, I think it's a cool feature, but maybe it was standardized too early. So maybe it's in the standard, it's being used, but I think without cache digest, it shouldn't be used, for example. So we're not having looked into that, but we're planning to do so.
Thanks.
Okay, thanks so much, Torsten. So next up, George Markdakis is going to join us to present some work that was at IMC in fall of last year about passively detecting black holing by listening in on the BGP. Hold on, just one second. Let me get this up for you. Okay.
Okay, thank you. Yeah, let me start by saying that the distributed denial of service attacks are still a serious threat, and every year becoming more and more dangerous, either for profit or for fun, or supported by national regimes and other countries. So when a network is under attack, even if a small number of the IPs and servers that hosted in the network are under attack, the network provider has to react. Because if it doesn't do so, there is a problem that the overall performance of the network may suffer. So one very cheap and available solution is to just drop all the traffic that goes to this targeted host. And this is called plug holing. And of course, you can do better because you carry all the traffic all the way to your network, only to drop it when it has already entered your network. And to achieve this, you use something that's called BGP plug holing. So you trigger the networks that send the traffic to you, stop sending the traffic, because anyway, I'm going to drop it. And what we did in this study is to see, by collecting data from different sources, if we can actually infer this in network data, and we can have some insights about who is using that, how often, how popular is this technique. How popular is this technique in general? So for the BGP plug holing, when you trigger your network that sends you the traffic, the network can also drop the traffic earlier. And to do this, one way, which actually I would say the default way, is to use BGP communities. So when you advertise a prefix that is under attack, you add in the community field a value, which is a 32-bit, where the first 16-bit annotate the network that has to drop the traffic, and the second 16 bits is a number that is used to annotate that that all the traffic to this destination has to be dropped. Unfortunately, this is not standardized. There are ad hoc solutions, and there is not a common dictionary that we can use for this. Now, some terminology, the prefix that will be black hole, the black hole prefix, the community is the black hole community. And essentially, by doing this, you try to drop the traffic much earlier. including the legitimate traffic. Now, the same thing you can do actually if you are in an IXP. In this case, the IXP provides the black hole community to the users, the members of the IXP, and by announcing the prefix to the route server, with this community, the members that participate in the route server can hear about this announcement, and then essentially the IXP has a null dump that drops all the traffic. In this case, the IXP is the black holing provider for the black holing. Okay. Now, let's see what is the difficult problem that we have to tackle in order to do this in reality. As I said, there is no common dictionary of communities. I worked with very smart people. We try to find ways to create a dictionary for communities. Is almost intractable. So the only thing you can do is you can go in case by case, for example, for black holing or for location or for other traffic engineering properties, and use some of the keywords in order to search, list, in order to infer communities. For example, here I saw the level 3 peering page or the geeks page, and then you can see that actually with simple data mining techniques you can find what's the black holing for them. So we did this and we found approximately 400 black hole communities, 50 of them in IXPs, and then we use that to analyze passive BGP measurements in order to infer black holing activity. So what we do is that we have a list of communities. When we see an announcement with this community in some of the BGP collectors where we have access to, we tag this, and we tag also the starting time, and then we wait until there is a withdrawal, either implicit or explicit, in order to identify a black holing event. And then we do this everywhere in the internet we have access to this type of data. Now, let's see the trends in the black holing activity. Here I show you the sources that we have used for this study. Of course, as many other researchers, academic researchers mainly, we use Riper route views, but we also use PCH, which is the route server PGP feeds, as well as the PGP feeds from a large CDN. And for the case of black holing, we were able to find 3 times more black holing events from the CDN and the PCH dataset compared to the other 2 Riper route views. In total, we use something like 13,000 PRIPs and approximately 3,000 PRIS. Now, one of the big observations is that indeed the use of the BGP black holing is on the rise. So we expect that as the number of DDoS attacks increases, the number of providers that are willing to offer this as a service increases. And indeed, during the less than 3 years of this study, we saw more than a 250% increase in the number of providers that provide black holing. More striking is the increase in the number of users. By users, I mean the networks that actually ask their providers to drop traffic. This is a more than 400% increase. And in terms of prefixes, there is a more than 600% increase. So the last years, we have seen a steady increase with peaks that I will explain later. And on average, we have 3,000 to 4,000 events per day, at least from what we see from our data. And these peaks are actually correlated well with high-profile attacks. For example, attacks during the Russian coup attempt, during the Olympic Games. And you see also a shift in the summer, fall 2016 that correlates well with the Mirai attack. Okay, now the next question is how efficient is the black holing? In other words, if I want to drop the traffic to a destination, how many hops can I save by doing this using BGP black holing? So what we do is that we get a signal that the prefix is black holed. and then we do trace route there. And then when we get the signal that the black hole activity event is over, then we repeat the trace route. And then we want to see how many hops in terms of IPs or AESs we have saved. And for this, we use the right patterns. So in this plot, I show you that on average, we save 5 IP hops and 3 AES hops, which means that a simple triggering with BGP black holing can save the 3 networks to carry traffic that has only to be dropped later. And this is also, on an academic at least point of view, a very nice way to show how networks can collaborate with each other when there is an attack undergoing. Now I'm going to spend maybe the last minutes, right? I have 2 minutes, 2 minutes?
Yeah, a few minutes.
The last few minutes in order to show you some insights about who is using black holing. So it's not the big users. It's not very popular in many countries. Of course, it's popular in the US because it has a huge ID, but it's particularly popular in Russia, and it's becoming even more and more popular in Ukraine and in other Asian countries. We have seen also that there is a huge difference between how many prefixes each provider black holes. So there are some of them that just black hole a few tens, but there are some that black hole thousands or tens of thousands. And also in terms of black holing users, again, we see a concentration in Russia, Ukraine, also Latin America, and most of the users are content providers or cloud providers. And this is somehow expected because those are running the big farms of servers. So when we did the in-depth analysis of what is running behind that and who is actually affected by black holing, we see that mostly are HTTP services, but there are also other services that have to do with mail servers, etc. But most of them are in cloud providers. And most of the domains are low-ranked domains. So it seems that black holing still is a mitigation technique for the poor. Probably others have used other mitigation techniques, for example, scrubbing, that is not visible in our data. Now, I will conclude just with one interesting observation. Something that we saw many times is that some of the black holing events last for hours, days, we have seen even months, but most of them last for a few minutes. And this was a striking observation. When we talked with people that did security, they told us that yes, indeed, most of the attacks are short lasted. They last for a few minutes. And another thing that we found is that many times when you run black holing, because you are not sure when an attack is over, or you're not sure that you want to penalize this IP forever, you just do an on-off. So you just activate it, deactivate black holing all the time. And this actually was very visible in our data. Okay, I will conclude here, and I'm open for questions. Thank you.
Thank you. Because you've been quick, we have time for a few questions. Thank you.
Hi, Alexander Azimov, Kyoto Labs. I just
Could you get a little closer to the mic, please?
One more time. Alexander Azimov, Curator Labs. I just want to highlight one thing that unfortunately black holing becomes a service. It's not only a DDoS mitigation, it's also a service for censorship. And especially in Russia, black holing is used to block some resources. And it is quite popular.
So let me see if I understand this. So you say that black holing is also used for censorship or for other?
Yes.
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 So I didn't want to say that. You said that. Fine. So now
you censored yourself.
Indeed, some of the long-lasting ones are candidates for censorships. We have enough indications for that, but we don't have a ground truth. So what I can say right now is that, like, if you see days of black holing, and also we use DNSDB and other tools that we can actually find out what this IP runs. Some of them are websites of political content.
Yeah, yeah, and it just will, you know, it looks like black hole plus hijacks in this way.
Okay, I haven't thought about it yet.
All right, thanks a lot, George.
Thank you.
So now we're getting into the part of the session where we talk a little bit more about tooling and less about measurement data. There's some measurement results as well. So first it's Kevin talking about how to use multipassing or how to measure multipassing with traceroute.
I think it'll be there in a minute.
Okay. Is it okay? Everybody can hear me? Okay. So I'm Kevin Vermeulen, PhD student at Sorbonne University, and I'm going to present ongoing work in collaboration with RIPE and CC and Steven, present in the room, about deploying MDA traceroute on RIPE Atlas probes. So this is a presentation that we've made at CAIDA for AIMS. And so first of all, I will give you a short recall about what is multipass detection algorithm and what its limits. And today I will mainly focus on, the goal here is to provide a better MDA. And for that, we have done, and we are currently, it is an ongoing survey that and I will present the first results that we have here on the load balancers and the data that we found in our survey. So for those which are not familiar with what is multipass detection algorithm, so it allows a user to discover all the paths between a source and a destination. It is based on Paris traceroute. So it is an extension to Paris traceroute. It provides some strong statistical guarantees on the discovered topology, but it potentially sends tens of thousands of packets to discover all the topology. And for that, it makes a worst case hypothesis that every discovered interface could be part of the load balancer. So what we've done here to answer the problem of sending too much packets, so the first step is to provide a survey, and for that we have sent so 350,000 trace routes toward destinations from impact IP hit lists, and we have divided this work between 35 Planet Lab nodes. So today, approximately 100,000 trace routes are computed, and by computed, I mean extract all the patterns that we can find in the trace route in terms of what diamonds do they contain and how it looks like. So what we found, so we defined some metrics. First of all, the diamond length. So here, a very easy example, where the max length equals the mean length equals 2. And on the right, the distribution of the max length. So we can see that mainly the diamonds are max length 1. And also we can see that the power of 2 are more current than not other lengths. And that is one of the diamonds that we found in the data. So with a maximum of 17, so with the source and the destination corresponding. And for us, it is important to understand what's behind this. So if anybody could explain us what happens in the network, if there's network operators here, we're pleased to talk with you. So the second metrics that we've defined is diamond width. So the width, and we provide also the distribution that we found in the data. So we see that there is diamonds with a very large max width, and in particular this one that we have found. So yeah, so here the max width is 96. So and the destination and sources are provided. So this is totally IP level and not without alias resolution. And the last one that is important for us because it helps us to define heuristics to provide a better MDA is a width asymmetry. So here in the short example, the width asymmetry is 2. And we provide the distribution. And what is important to see here is that the width asymmetry are pretty rare. So for us, it's a good thing to take into account. And here also, so here the max width asymmetry is 39, and you see, in fact, that there is, so in red there is a source, in green there is a destination, and there is completely 2 divergent paths going into, so one going into 2 clustered area, and the other one going into a simpler path. So here also, we're pleased to discuss with network operators to understand better what is going on here. And the last metrics that we have defined is the meshing. So, and we are defining some more meshing metrics to also improve our heuristics. So this is an example of so the diamond on the right has a percentage of meshing of 95%. So it's what we have found in the data. And the last one, just to give an example of when you unroll a topology hop by hop, the MDA uses 8,500 packets to discover all this topology. So that's why it's important for us and in a constrained environment such as RIPE Atlas to make this figure lower. Okay, so do you have any questions?
Yeah, it looks like well, we've got a couple minutes for questions if anyone has one. Anyone other than me? Thanks, Kevin. I think I don't know the literature here. I think it's interesting that to contrast what you found with this breadth of paths versus what we usually call the diameter of the internet, right? We usually say the diameter across the length, basically, of the trace. We see a maximum length. What do you know? What can you tell us about? Is this terminology with diamonds and things something new that you're creating with your project, or is there an existing literature about it? And can you compare? So you said you used 80. Well, that's the first question. Is it your terminology? And
yes. So there is a paper from Brice Augustin in transaction and networking, which has done a survey also almost 10 years, 7 or 8 years ago, and he defined some metrics that are present here, like length and width, but we have added the symmetry and meshing because for our heuristics, these metrics are important.
Thanks.
Hi, Kyle Rose. Do you think that this information or these techniques could be used by an attacker to discover weak points in the network? In particular, if there's a wide node, you know, that could mean something, or if there's a non-wide node that could mean something. And could you, as an attacker, try to target a specific load balance node and take it down because you have identified it as a bottleneck, for example?
So, well, I'm not in the security at all, but well, maybe, I suppose so. The goal here was to make an AS map. So by merging all the traceroute and MDA traceroutes that we get, indeed we see some, we see where is the core of the network, and maybe yes, you can serve such purpose.
Yeah, Tim Chan, thanks very much. It's very interesting. I regularly use a package called PerfSonar. I don't know whether you've heard of that, for measuring loss latency and throughput between quite a large number of sites. And one of the issues there is its trace task has no idea when the path changes, whether it's in the local site, the fast site, where the measurement nodes are hosted, or somewhere in between. And I think the interesting thing now is to understand, just simply from an algorithm, is it something in the local site? Is it something in the fast site with ECMP or whatever? Or is it something in the middle? Then actually having just a classification of which of those three it is would be very useful in itself.
So what's the question?
Sorry?
Can you repeat the question, please? I didn't.
I think one of the interesting things you could get from this is to be able to have some heuristics to determine when you're doing a measurement between measurement points in two sites, using whatever package it is that does some kind of trace. Is it a change in the path in the local site? Is it a change in the path in the remote site where the device is hosted, or somewhere between those two sites? So if your heuristic is going to be applied to that, that would be a very useful thing for people using tools such as PerfSonar, I think.
Yeah. So the heuristics at the moment don't take into account where the load balancing is taking place, such as is it at the beginning of the path or at the end of the path. But it could help. It's a question that we've thought about.
I'll try to email you an example of what PerfSonar does and how it visualizes changes in paths and how your approach might help it. Okay, thanks.
Thanks, Tim. And thanks, Kevin, for joining us with that. All right, we're up to the last of our presentations for this morning. And we've got Olivier Timmons up, who will take us through our lunchtime, or up to our lunchtime.
Okay, hello everyone. I'll just to start by giving just a quick recap of what we have in our campus network, because that's the main motivation for this work. So our operators, so that's the university campus network, have two ways to understand what's happening: NetFlow logs and some logs in the DPI or the firewall. That's about it. Now there's this thing that's been popping up a lot over the last few years. And if you don't recognize the sentence, it comes from there, basically. If we start to encrypt everything, looking at NetFlow traces or DPI logs or stuff like this won't be useful at all in order to understand what's happening in the network. Do I have transmission? Do I have losses, reordering, these kind of things? Seeing the debates that's been happening in the quick working group for just one bit in the clear does not make it look like it will be easy to understand about anything else about it. And so basically we want to be able to troubleshoot the network at our scale, and we have no visibility of the traffic. So the main insight we have is that the NOs know everything about the connection, be it for TCP as of now, but for Quick as well. Your browser sees everything in the clear before encrypting and transmitting. So if we had a way to instrument the host to get the information out of it, get exactly what we want out of it, we would be able to troubleshoot anything. The issue with that is that so far we have MIPS, so the TCP MIPS, for example, to query counters to SNMP. And again, that's about it. So we have an issue there where we want to get visibility, insights over the traffic, and where we don't have it. What we've been working so far on, well, here, the thing I'm presenting here is a tool on which we have been working, which tries to probe, to instrument dynamically and host, so computers, and look at, for example, the TCP stack in the Linux kernel, or DNS resolution routines in the libc, and do this at runtime by injecting some code that will just feed back measurements towards some user space daemon. Once you have this data that gets extracted, you can just export it, again, over generic serialization formats such as IPFix. You don't want to export anything. You want to export stuff that we're able to understand, and that should be that you should be able to apply to about any protocol. So we extract transition for state machines. So think statistics about what has been happening in the TCP handshake, and then once the connection has been established, what happened over there, did we see loss, retransmission, this kind of thing. And we look for very specific bits of information that we can extract directly from there. So that's a high-level overview of the tool, and originally we wanted to stop there, but then we deployed it. And it turns out that doing a deployment is quite interesting because you learn stuff about your network that you did not expect to be there. So we push this on every single machine that the students use in our labs. Because the student mainly browse Facebook, Google, and this kind of stuff, we have traces toward these services. These are mainly TCP and DNS traces because, well, Quick is still a bit hard to instrument so far. That's a work in progress. And I've collected here data from the past month. And maybe just as a final comment, we have a network that's vastly over provisioned, so we don't really see a lot of big issues, but we still have a few. So this is a plot that shows the amount of flows we got over IPv6 and IPv4. And so as I said earlier, students browse Facebook and go on Google. And so these are geostacked services. That's the data we get from there, hence the IPv6 peak. For all the next graphs, the colors should match for IPv6 and IPv4, and you will get points every 12 hours over the month. I care about IPv4 and IPv6 in this particular example because in our own network, these are routed over different uplinks. So these may exhibit differences. And so the first performance point that I tried to look into was, did we have connection experiencing word losses? So in this particular case, were there connection that were losing some TCP SYNs, for example, when they're trying to establish a connection? And how was it comparing across IP versions? Well, that's the result here. So we have actually some connections, so that's a tiny amount, where it's distributed evenly over IPv4. And when you look at the destination addresses that were targeted by this particular connection, these were uniform. So without any particular bias towards a given destination. Nothing was happening over V6. If we filter the data and check only connections that had more than one lost SYN, then all of a sudden everything disappears. So we have something in our own network that appears to be, I don't know, overloaded or dropping some SYNs. We don't really know. And it's small enough that when we query our network administrators, they actually don't even see it because that doesn't appear in it's too small to be flagged in their data logs. So that's just one of the points that we kind of noticed it that we didn't expect. And that's a super simple query to run once you are able to get data directly from the host.
Could we pause just 1 second? Spencer, did you have something that interrupt here?
I'm Spencer Dawkins. I'm the responsible area director for Quick, among other things. And I just wanted to say that I find this presentation fascinating. Thank you.
Thanks for the comment.
Anyway, continue.
Just to make sure, we also looked at connection that were just failing, and there, the network works, and that's what's happening here. We have a small spike there that we investigated, and actually all of these connections were linked to some weather applets that was running on every student's computer, and that was that basically we didn't know what's actually over there and doing queries, so we have to clean up a bit the network. If we move from just, I don't know, lost initial TCP SYNs, we can look at TCP RTT. So these are median smooth RTTs as extracted from the Linux kernel directly, and compare it over, for example, IPv4 and IPv6 and across cloud providers. So our students use Microsoft services to get emails, to use on the online Office suite. So we know we'll get data over there, while Google, that's how they work. They Google the question. But if you look at the RTT over there, well, we actually, again, have no clue as to why do we have such a vast difference between two services that appears to be present in both IP versions? So that's yet another data point. We need to investigate in our own network. And especially because we are starting to speak here about latency, about RTT, that's something that we, well, at least our operator had no knowledge about because they could not track it. Their spike, we don't know why, but it's fairly large. If we start to compare jitter across, TCP jitter across address families, so remember that V4 and V6 are routed over dedicated separate uplinks. Again, we observe stuff. We actually really need to take a deeper look at what's happening in our own network. So far, all I've presented are results that are tiny, that currently have no widespread impact because people are not complaining that much. But looking at all of the data we analyzed, these were kind of spikes, so that were not expected. And if our network was to be more used, I don't know, this could start to raise issues. I'll conclude the talk with just a recap of something we actually had in February. And so for once, we got complaints. So students were having issues to reach the online course platform, so Moodle, and they're just telling, well, it's slow. It takes it's way slower than usual. And so how do you get around troubleshooting this problem if you just have data that you can browse through? Well, that's very simple. You know that they'll do DNS query, so they'll use our own DNS resolver. So we can just look at, for example, the time to establish, the time it gets students, the time it took students to get a DNS reply from the servers that we know are collocated in the same data center that web servers, and compare it to the time to establish, so the time to get the SYNAC from the TCP load balancer over there. But if you notice over in this particular data, the data center was 200 meters away from the host we were instrumenting. And so I'd guess that 30 milliseconds for just 200 meters, probably not that great. Once the problem got noticed, well, that was a load balancer that was overloaded, etc. So that's up stuff, but it actually disappeared. So we know it was literally just that because the problem is fixed. And so just as final thoughts, we built a generic approach, which actually I did not get into detail there because that's academic formal stuff for state machine reduction, these kind of things. We have a prototype that instruments stacks that students currently use on our network because that's what we care about. We have a prototype for Quick, but there are technical challenges to deploy it over there. But the main question I'm asking is there interest for kind of an event-based reporting, monitoring mechanism for transport protocols, especially if we start to encrypt? Because we can't have a middle box sitting in the network decoding everything. That's not feasible. So how do we get around extracting the data and analyzing it? That concludes the talks. If you have any comment or questions, or maybe hints as to why we have a network that has crazy behavior, I don't know.
Okay, thanks, Olivier. You wanted to say something? Yeah, there's a question back there. We've got about 7 minutes, so we'll be able to answer those, and then we'll close. I think the mic might be off back there.
Just for one mic.
Tim, do you mind if we have him?
Sorry, Tim Chan, just a quick question. Is the code available openly on GitHub or something, or is it private at the moment?
If you want it, I can give it to you, but it's not yet published, so I'd rather keep what we have. But I'm fairly open to just deploy it elsewhere and compare data points.
All right, thanks. I'll pop
I'll
in
have issues with sharing the data set, though, because there's privacy implication for the students.
Lorenzo Colletti, what are you using? The C group BPF filters?
I'm sorry?
What are you using? You said eBPF. Is it the C group filter?
So that's that part. So I'm targeting so far Linux machine, and so I'm putting kprobe, so probe tracing mechanism in the kernel attached to whatever function.
Oh, so you see socket calls. So you see socket. So you see socket calls, not packets.
No, I don't use. Well, I can. How to make it simple?
You don't have to make it simple for Lorenzo. Just say what it is.
I'm attaching Kpro, so I'm remap emitter setting any code done in the kernel on any function, and I'm able to then run arbitrary code to
Okay.
the memory and extra values.
So then my question actually is, what does this give you for Quick? It shouldn't give you anything.
You can do that in user space as well. You can do that for user space process as well, and so that's what we did for an RTP library for Go, where as long as you have the symbol, so you can compute the offset as well at the front end.
No, thank you.
So basically, you're saying that you have to do something like either LD preload or whatever to attach.
Not even actually. So we can set up the kernel such that any be it user space or kernel space call matching some symbol will have a soft interrupt attached to it.
So your instrumentation only works for a given version of the Quick binary.
That's actually a change we have with Quick, which is that we have 12 implementation, and so if people start at, well, it's literally a target for our network. So we know that students, for example, here in our infrastructure have Chromium. We have the symbol, we can instrument that one. If we want to move to another implementation, we need to make it compatible. And that's the struggle here. We need to define what would be a better way, not to reason on a per case basis, but have a generic way to instrument protocol.
But like it could break between Chromium 65 and 66, right?
I'm sorry, what?
It could break between Chromium version 65 and version 66.
Yeah, but since we own the machine, we own the version that's there. We control everything, so we can.
All right. Okay. Thank you.
Let's throw out the last two questions.
Neil Cardwell, Google. I just wanted to offer a conjecture on the mysterious delay spikes in some of the graphs. I noticed that and some of the TCP RTTs you're seeing were suspiciously similar to delayed ACK values on common operating systems of 200 milliseconds and 40 milliseconds. So that would be one thing to look at. That one was 40 and that one's 200. That's one. I don't know if you look.
I think you said you went on to offer some insight or commentary about the spikes, right?
Yeah, that they might be delayed ACK timers firing at 200 milliseconds in this trace, and then 40 milliseconds on the next page would be something to look at. Yeah.
Teresa Enghart, TU Berlin. Thanks for the very interesting talk. I'm sorry if I missed it, but where can I find your code?
So if you want to run it and deploy it on your own infrastructure, I can give you links privately, but so far it's not published. I can't make it available already. But I'm free to, I'm fairly open actually to just collaborate because it gives more data and more stuff to reason about.
All right. Thank you, Olivier. So just in closing, you might have noticed the last two talks were a little different than the earlier ones. If you didn't notice, the way they were different is they're a little bit more about the measurement tool or the strategy. And in Maprg, we specifically say we want to bring measurements that provide insights to the engineering of the protocols or the operation of them. So if you have thoughts about that, you can share them on the list or with us. But we basically suggest that you can only come and talk about a tool if you brought a novel measurement for us. Thanks for joining us for the meeting, and we'll see you in Montreal, we expect.
Yeah, so thank you for being so much on time. And if you have any feedback on the agenda in general, what you would like to see, what you didn't like, please let us know or send it to the mailing list. Thank you.
All right, so I'm going to get this back there to the sound guy because it needs a battery.